You
Okay.
can
I've got a laser pointer.
yeah, you've got a laser pointer. You
And it's
can
quite a
you can
big
fix
room.
it on the wall. Yeah.
What
and
are you
it's quite a
guys
big room.
talking about?
General relativity.
Yeah.
Okay.
Yeah.
So I'm
Anyway,
sure-
so Einstein was the master of thought experiments. He really liked doing thought experiments, thinking about the way the world works. And he was thinking about what would happen if you were in some sort of elevator or rocket accelerating upwards. You would feel a force downwards, the way that you do in an elevator when it starts moving up. And there's no experiment that you could do that could tell the difference between an elevator in space moving upwards at 9.8 meters per second and an elevator sitting still on the surface of the Earth. You'd feel the same. Every experiment you could do would be the same. And so Einstein said, well, let's make that a principle of nature. We'll call that the equivalence principle, that gravity is equivalent to acceleration. But if that's true, if you shine a beam of light,
My laser pointer.
yeah, your laser pointer, that's going to get bent, right? Because it's going to travel in a straight line, but you're moving upwards at faster and faster rate, and so it's going to curve toward the floor. But everything has to be the same in a gravitational field. Everything has to be the same if you were standing still on a planet as it does if you were in a constantly accelerating lift. So Einstein realized that this meant that if the equivalence principle is correct, then light would bend due to gravity in exactly the same way that it would bend due to constant acceleration.
But light can't bend because it.
Yeah, light always travels the fastest path between 2 points. So if light's bending, that means that space and time have to be warped.
Well, I get why space it has, but why time?
Because special relativity says that if you warp space, you have to warp time. Special relativity says that space and time are inextricably linked.
Right.
Because one couldn't exist without the other.
Yeah. Well, and also there's disagreement. One person's space is another person's time. You can have two events that happen, and two different people looking at it from two different what we call reference frames. So one of them moving at different speeds, and one of them will say, "Oh, the time between these two events was 5 seconds, but the distance between them was 20 miles," and the other person will say, "Oh no, the time between them was." I'm not going to get the numbers right. The other person's going to say, no, you're wrong about both the time and the distance between them. But they'll agree about sort of the combination of space-time between those events. There's not that complicated mathematical formula that you can write down that's for something called the space-time interval between these two events, and that these two observers will agree about that formula between those two events. And so this indicates that the real thing that's going on is space-time, and space and time are just sort of aspects of this deeper concept.
So we know all the bending of all the space and all the time, and everything's warped.
Yeah.
What can we apply this equation to? Like, what use does it have in the real world?
Well, for one thing, without general relativity, we wouldn't have GPS. Because GPS satellites are much farther away from the Earth than we are, here on the surface or close to it. And as a result, we feel the Earth's gravity warp time more than the satellites do. And so the clocks on GPS satellites run at a different speed than the clocks on Earth. It's not a big effect, but it's big enough that if we didn't compensate for it when, computers on Earth talk to the GPS satellites, if we didn't compensate for the difference in the speeds of the clocks, then GPS would start drifting noticeably, and we would get the wrong answers from the satellites
Turn left at the next junction.
within, I think, a few days.
You have arrived at your destination.
What relativity, both special and general, tell us, the lesson that they teach us about time and space, is that they're not independent of one another. That's really the lesson of special relativity, and the lesson of general relativity is that neither space nor time are independent of the masses and the things, the mass and energy, that live in our universe. That the things in our universe can affect both the space and the time around them.
Neat.
Questions that we ask are a function of the quality of our theories, and as we get better and better theories to get us better and better approximations to the way that the world actually works, we end up asking more and more detailed and strange and bizarre questions about the weird place that we live in.
We could call it that. We call it questions for Adam.
Adam's questions.
Yeah. And then people could submit questions if they want, and we can ask them like physicsy type stuff. Do you understand it? So okay, cool, great.